Good afternoon, good afternoon, good afternoon, good afternoon, good afternoon. Welcome back to COMP1511. It is week 9. This is lecture 16. You have all just had a fantastic assignment come due. I've got to say, I am so excited to see the number of you who were blogging about the joy at the end of the road for that assignment, that overwhelming, wonderful joy of having that assignment finished. So I do hope you all enjoyed that assignment. I personally think it's really quite beautiful as assignments go. The reflection for that will be coming up in the next couple of days. There is also a wonderful little activity called Mandelbrot, and that also closes on Wednesday. We'll have voting after that closes for the most beautiful images, but let's just have a quick look at some of the images that are already up here. There are some truly beautiful images that have shown up here already. So these are honestly just so beautiful. I could just look through them all. Okay, aside from the occasional glitches, there are some truly beautiful pieces of artwork here. So, for those of you who have submitted, all 149 groups who have submitted, you are all awesome. Your artwork is, wow, that's gorgeous. Your artwork is, on the whole, absolutely fantastic. There are some really beautiful submissions. So if you haven't yet submitted, if you haven't yet found Xanadu and shown off your beautiful colour scheme, you've got a couple more days to do that. There are some truly beautiful things there, but we'll leave that for the moment. I should also just quickly mention, in case you've forgotten who I am from the 2 odd weeks where I was lecturing, my name is Jashank. Andrew is extremely unwell today. We have sent fresh water and hole drilling supplies because he's unwell. Oh, very good, very good. Oh dear. So when we last had you all here on Wednesday, we were talking a lot about abstract data types, this weird and wonderful thing where we're able to separate an interface comprised of opaque values and all these details are hidden from the user, but there is a well-defined interface, a well-defined set of rules by which you can interact with our ADT, and we talked about separating that from an implementation where we actually had an actual structure. We were able to manipulate data and define how these behaviors worked. We talked a bit about how we test that, and that you shouldn't trust the implementation, and the implementation shouldn't trust you, the user. This is what an interface might look like for a complex number type. We don't know how this stores values. It could store it as a real part, an imaginary part, or it could store it as a magnitude and phase if it's an electrical engineer. We don't need to know, though. We honestly do not need to know how that data is stored. The implementation, of course, we actually sit down, implement those structures, implement those functions. In this case, this version of this structure, or this version of this implementation, does actually use a real and imaginary part. And you can guess that the complex real function, and the complex imaginary function are getter functions in their new ADT jargon. They allow us to retrieve a value out of the ADT. And of course, complex mod and complex arg actually have to do some calculation. They have to take a square root, they have to take an arctangent to actually return that value. But if we changed this, so instead of storing a real and imaginary part, we stored a magnitude and a phase, you can see that we would have to use, in or complex mod and complex arg become, of course, just getter functions in exactly the same way as complex real and complex imaginary were. But of course, complex real and complex imaginary would now have to change. They would also have to do a calculation. They'd have to do the r cis theta calculation. And of course, you decompose that. But it doesn't really matter how you implement it. And really, some of you are probably going to be asking yourselves, why do we have this thing? Why do we have to go to all this effort of splitting our code up into multiple files, of defining these interfaces, of going through and testing them? What do we get that we didn't already have? And this is actually one of my favorite quotes by a guy named Edzer Dijkstra. And if you're going to be in the field of computer science for any length of time, you will come to know and love the name Edzer Dijkstra. Edzer Dijkstra wrote these beautiful texts, these beautiful monographs, handwritten in the 1960s and 1970s, about programming and the beauty and the art and the joy and the craft of programming. He banned GoTo, amongst other things. He also came up with a whole bunch of new algorithms. He was really one of the people who founded computer science as an actual science. It used to just be maths and electrical engineers. But Edzer Dijkstra wrote this whole stack of monographs, 1,318 of them, all handwritten. You can see most of them on the web. They are repositories of such wonderful wisdom, and if you have time to do so, I highly recommend going and reading an EWD paper. But in EWD 340, because they're all catalogued, of course, in exactly the same way that the works of a classical composer might be, he talks about abstraction. And we've talked a little bit around abstraction in this course up to this point. We've not really sort of attacked it head on. And one of the things that, this is the reason this is my favorite quote by Dijkstra, is that he talks about abstraction as a tool not for being vague, not for waving your hands around and saying this is all just sort of, this will come out in the wash. It's not to do that, is to create a new level of clarity, a new semantic level in which you can be absolutely precise. You don't want to be stuffing around with stabbing pointers and dotting structs and indexing arrays. You want to be saying things that you are trying to achieve. Functions, up to this point, have been your unit of abstraction. Get local time, you might decompose into a function called identify time zone and add time, as an example. Our escape steps, we saw we had functions decomposing down from that, complex add, complex square, complex absolute. But going back up further, we also had escape grid, draw Mandelbrot, serve bitmap, all of these functions in this stack that served to form new levels of meaning, new levels of semantic state, where you can be absolutely precise about what it is you mean to do. Yeah? You mean to add two complex numbers together. You don't want this wall full of z.re is this and this and this and this and this. z.im is this and this and this and this and this, and a little bit of this. You're adding two complex numbers together. That is otherwise obscured. This is a very philosophical thing. This is a very craft and science and art of programming thing. But creating a new semantic level where you can be precise means your code is more beautiful, more clear, more maintainable. If I were to look at your getLocalTime functions, going back to assignment 0, I love assignment 0. I'll talk a little bit more about assignment 1 and how we can make the same statements. But going back to assignment 0, how many of you remember your assignment 0s, by the way? Just sort of you can... Okay, that's not too bad. So if I were to say, if I were to put out, if I were to put the question to you, what if I were to change the specification for that assignment? If I were to take that assignment specification and say, you have to handle more time zones, how many of you would have to make huge changes to your code? And by huge changes, I mean you would have to go through, change every single if statement or half of the if statements you have in your program. You've got to go through, beat your face against all of these weird bugs again. If I were to change the spec and say time zones could be negative, how many of you would have to go through and massively change your code? If I were to go through and add the requirement for years, you would have to handle daylight saving time across years. You'd have to work out where the last Sunday of the month was. How many of you would have to make radical changes to your programs to do that? Yeah. This is what we mean when we're talking about this obscuring the solution in the details. You're losing the trees and seeing the forest. You're seeing this forest, this spaghetti of code, and you're losing the individual details of how you solve that problem. So, one of the things you will do, actually, with assignment 1, in that reflection, you'll be talking in that final reflection about design, about abstraction, how you would change and adjust your implementation. So I highly recommend thinking about those things, about abstraction and design, especially with assignment 1, with that final reflection. But now, as we're starting to play with ADTs, let's talk a little bit more about why we want this new level of meaning. Yeah? And we can see how ADTs give this to us, because instead of having to reason about these really hand-wavy types that are all just sort of slung together in a vacuum, we can talk about a thing now. We can talk about, effectively, an object now. I could create an ADT, I can manipulate that ADT in exactly the same ways as I would any other data type, but I now have new ways to state how I'm working with it, clearer ways that allow me to state my problem and my solution more clearly. So, let us fill this room with concrete. By which I actually mean, let's actually do a demo. Let's play around with a whole new concept actually. But it's a concept that we've actually seen a bit before. We're going to play with stacks. It's going to be stacks of fun. Stacks are a data structure. The first of the sort of proper data structures we're actually going to play with in this course. A stack is a structure where you have the last thing you put into the stack being the first item that comes out of the stack. That seems all completely reasonable when I state it like that. And we have these operations around stacks. We can push items onto the stack. We can peek at the item that is on the top of the stack. And we can pop the top item off the stack. Very, very simple, clean operations. You can sort of reason about these fairly easily. I can state these to you. You can see in places, some of you probably can, why we would want this stack notion. Why we would want to talk about this abstraction of a stack where the last thing I put on is the first thing that comes off. So let's flip over to VLab now. And let's implement a stack. Maybe. Which keyboard layout am I in? Oh well, I'll just crash X screensaver, that's fine. That's not meant to happen. Anyway, disregarding the fact that everything in this reality is broken, let us have a look at a concrete stack. As before, we have a header file, and a header file full of hash defines and type defs and prototypes that expose for us an interface, yeah? We have here, of course, a concrete type, so this interface will look a little bit different to the abstract types we've seen. And we'll take it towards an abstract type at the end. What we're going to have is we're going to have a stack of characters. I push a character onto the stack, I push another character onto the stack, then I can pop those characters off the stack. Here. In this case, we've got a hash defined up here to tell us that our stack can hold 1,000 items. In a couple of weeks, when we see the last major chunk of the course, we'll see a really nice way to fix this, and we'll come back to this exact example. We also have a type def, and as usual, C is playing that weird game with us, where the type, the existing type, is a little bit everywhere. So as we remember, in a type def, the first part, this part up the front here, is the part of this type that is real, and the part following is the part of the type that is created by this type def. The problem with this type def is that the part of this type that exists also continues over here. So we have our type def character array. We're allowed to type def arrays. That's perfectly valid. In this case, we're type defing an array of characters that will be stack size in size. Yeah? And every time we refer to stack data, we're going to have a character array of 1,000 items. Okay. Now, we have 3 functions here that we have prototypes for. We have stack add, stack top, and stack pop. By convention, that is a typo on my part. By convention, we call this first function stack push or push, and the last one we call pop. These are sort of the 2 primitive operations on stacks. You sometimes get top or peak. They both serve the same purpose. They give you back the thing that is on the top of the stack. And all of these functions, with the exception of stack top, of course, stack push, stack pop, take an existing stack, modify it, and give you back a new stack. So you're holding on to a stack. What you get back is a new stack, and everywhere you're referring to the old stack, you should now refer to the new stack. Yeah? This is this notion of mutability and immutability. The notion here is that a stack by itself is immutable. You cannot change a stack. What happens is these functions do some magic and give you back another immutable stack. But they hide, they abstract that mutation. Okay, so the other thing we should talk about also is testing. Because the most important thing when you are writing an ADT, when you are developing its interface, yes, when you are developing an implementation, is tests. So what we're going to do is we're going to write up some tests quickly. I have here a stub called test stack. Fantastic. What we're going to do here, we have hash included our interface. We have also pulled in assert.h, which means we're about to have a very good time with asserts. Remember that assert allows us to state an invariant about our program, something that cannot possibly be false. If it is false, the program goes away. Simple. The program goes away, there's a nice crashing sound, and your program goes, here's something that went wrong. And at the end, of course, all tests passed, you are awesome. So, let us talk a little bit about our expectations of a stack. The first thing, of course, is because this is a concrete type, we actually have to declare it ourselves. We have to create our own stack. So what I would do is I'd say stack data. S is, I'll just set everything to 0. We have a character array, and we can already start to see problems appearing, because as we've got our character array, how do we tell if a value is in use or not? We can't really. So now what we're going to do is rethink our interface. What we're going to do is we're going to change our interface. We're going to add some constructors. And we're also going to change our types a little to make this a bit better. The first thing we're going to do is we're going to take our stack data type, we're going to burn that to the ground. Instead, we're going to replace it with a concrete stack type. So we're going to have type def, of course. We're going to have a structure, and we're going to call it underscore stack. And of course, because this is a concrete type, we're going to call it, again, stack. So we type def structure underscore stack as stack. So what are we going to put in it? We're going to put in some data. This, of course, is going to again be a character array. It's going to be stack size in size. Another thing that's probably worthwhile mentioning is how big our stack is, because let's say that our stack isn't going to be that big. So we would explicitly say, we might like to anyway, explicitly say how big our stack is. And when we dynamically allocate this, we'll see why that's really, really nice. And of course, we want to know how many items there are on the stack. Okay, so we have an array of elements, which is an array of characters. We have an integer size, which is the size of the stack. We have an integer number of items. Now, we could just say the user of our stack is responsible for looking after this. We're not going to bother. So we'll do that. And so now it is the user's responsibility to say the elements is all empty. The size is stack size, and the number of items is 0. Ugh, this is horrid. Anyway, let's continue, hopefully, without things exploding too much further. We're going to write some black box tests here. We're going to assume that everything else about the interface is hidden. Black box testing, of course, is one of our 4 types of testing. The 4 types of testing we have are, of course, the bad tests, which you'll notice I'm carefully avoiding here by writing my tests first. We also have, black box tests, which we're going to write here. We assume that our implementation, that our thing that we're implementing is entirely abstract, and we can just treat it like a black box. We put a value in, something comes out. We have white box testing. This is sort of reaching a bit towards it, where we explicitly set up some state, and then we test that state after we change it. And then, of course, there's unit testing, and we'll come to unit testing once we have got an implementation. Because, of course, we don't have an implementation yet. Okay. Stacks like this one, we can't pop off this stack. That would be invalid, because there's nothing on this stack. We can push items onto this stack, though, and the way we'll push some items onto this stack is by calling the interface function, because that's the way you do it, right? I mean, because this is a concrete type, we could just reach in and say, hey, stack elements 0 is actually the letter Z. I have an updated number of items, so I now can't use the stack interface functions, because presumably they all depend on items being updated. They presumably may depend on some other state. They may presumably depend on the phase of the moon, for all I care. So we're going to use the interface. So we're going to push onto S the value that is the character Z. Yeah? Remember, of course, character, literals, single quotes, that gives you that character, that gives you that value right there. There's no ASCII values anywhere up my sleeve. Now, the other thing about this stack type, of course, is that this creates a new stack. So what I have to do is this strange contortion where I do S equals stack push onto S of Z. This is getting a bit contorted. Hello. What does stack push do? Stack push is one of our two primitives of a stack. Stack push lets us push a value onto the stack. This is now the last item that got entered into the stack. And if I were to now peek at the top of the stack, which I will do in a moment, this we can now assert that its value is Z, and if I pop, there are now no items on the stack. There was an extremely excited hand up the back there. There are two distinct things that we both call stacks, just to confuse you. There's the call stack, which most of the time we're quite careful to refer to as the call stack or the function stack. And then we have this notion of the stack as a data structure, and it just so happens that the call stack very much smells like one of these stacks. Conceptually, they're similar, but in purpose, there is a more well-defined purpose in the call stack. This is a much more generic thing. Where's an example we might use a stack, just out of curiosity? Anyone think of any good examples where I might use a stack? The last in, first out accounting method. Well, there's no accounting for taste, I suppose. Any others? To reverse a string, yes. That's an example that we've seen a couple of weeks ago. You just push all the values onto a stack. The last element that comes out is now the first element. Now we can use a stack to reverse a string. That's very good. Another place you might use a stack is when playing cards. Well, cards. Any sort of card game where you have a stack of cards. You pull the top card off the stack. Well, here's another good one. You know those Pez dispensers? They're a stack. The last thing is on top, that item comes out. And that effectively is the top of the stack. Yeah? So in this case, our Pez dispensary has the character Z on top. I can now pull that value out. Let's do that. And let's now assert that. So we've pushed a value into the stack. The top of the stack is now Z. If I were to push another value into actually, before I get too much further, what I would now do is assert that I can pop something off the stack. And again, the same weird contortion. S is stack pop of S. Now, for those of you who are awake, which I hope is most of you, you would have spotted I don't actually have any way to return the item that popped off the stack here. Because this weird mutability trick means I don't actually have anywhere I can return that. And we'll talk a little bit about how we fix that momentarily. But once we have some simple tests, a simple user, I may as well also check that, let's just hallucinate into behavior a effect, excuse me. Let's hallucinate into reality this behavior that when the stack is empty, the topmost item is 0. And now we can make that statement before we push something and after we push something, yeah? So what we have here is a very simple test. We push something onto the stack, we check what is on top of the stack, we pop something off the stack. Hello. What does stack pop the function do? It does exactly the opposite of stack push, we hope. Stack pop, again, is the other primitive of a stack. It pops the top thing off the stack. It pulls the top item off the stack, pops the top plate off the plate stacker, however you want to imagine it. Okay. So we have here a test suite, we have an interface. Can I go ahead and compile this? I see a couple of people saying no. I am a fool and will thus charge ahead and do so. There is a return exit success. What I will do, though, is I'll now mistype that. Oh, man. Okay, so now we get the horrifying screamings of the linker, no relation to one of our tutors, who, the linker here is screaming that there are all these functions I'm using, all of these functions I'm referring to that don't exist. So I need to compile in my other file, the file that I haven't written yet, so let's write that very quickly. So again, we have these simple interface functions. There they are. We can now, I should include stack.h. Okay. So again, I implement my stack, remembering that the shape of my stack is a bunch of elements, a size, and a number of items. So, stack push, what stack push is going to do is it's going to add this element onto the stack. Let me flip that over to being C. Like so. So I have S elements, I'm going to assign ELT into it. Now, where do I put it? Yes. Yes, exactly. S items +1? I've heard a few mutterings of +1. In this case, so long as we pick a behavior and stick to it, we should be fine. And of course, there is now a new item on the stack, so I can bump up the number of items I have. Probably also worthwhile checking that S items is still less than the size of the stack. So if it's not less than the size of the stack, then of course we can chuck a wobbly and end the program. All right, I'm going to use here because I like and of course I'm going to need stdlib.h to get exit failure. Okay. So again, here we have a warning saying we're pushing onto a full stack if the stack is full. Nice and simple. That's one of our functions done. Okay, how about another one? Stack top. That just gives me back the top topmost item, doesn't it? Okay, so let us go S items, index S elements at that, and return. And at last, we are going to pop an item off the stack. Again, we don't want to be popping off an empty stack, so we grab, again, our error handling for the situation where S items is 0. Because, of course, popping off a 0-item stack doesn't make sense. Popping off empty stack. And then what we can do, oh yes, one thing we have to do, of course, is return S. And again, here we're going to return S. And for this one, what we're going to do is we're going to do the opposite of what we did in stack push. We're going to take our element off the top of the stack and move the stack back down. So in this case, we're going to do it in reverse order. S items minus minus. Oh, we can't return a value, so all we need to do is set S elements, S items back to 0. Okay. Set it back to 0, like so. Let us now compile this. Once again, we have linker screening, but now we can compile in the functions we have just written. Ooh, success. Okay. For those of you who were paying attention, you would have spotted the errors I have deliberately inserted into this program, and here is an assertion failure, just to prove my point. So, we have an assertion that has failed. We have a test that has failed. This is how we develop and debug. This is a skill, actually, just before I go on, this is a skill that is extremely important to you if you're going to go on and do any sort of computing, really, even just to the end of this course. Learning to debug your code is the most important skill that we hope you have. Learning to look at your code, step through it logically, don't just randomly fiddle with stuff until it works. You will be able to debug your program. Okay, so what do we got here? We have this failing assertion that stack top is equal to Z, which means stack top is not equal to Z. That invariance, that statement of fact, is refuted. It's taken to be false by this program, and the assertion fails. So, obviously, we have a problem, which is, in this case, at the top of the stack isn't Z. So what we're going to do is we're going to go back to our code and have a look at stack top. Stack top takes S items as an index of S elements and gives me back that value. This seems really, really simple and clean, yeah? So, DCC has helpfully dumped out some useful information. If you don't have DCC up your sleeve, there are other debugging tools that are at the moment a little bit beyond the scope of this course. We may do an extension lecture at some point talking about how to debug without DCC. Well worth learning to do. But the most important thing here is we look at S. S's elements are Z, followed by 998 nulls. S's size is 1,000, as we expect, and S has one item in it. Now, we remember, don't we, our initial state. Our initial state is that, can I split this? Yes, I can. Fantastic. Let me fold this up and put that over there. Okay. What we're going to do is we're going to walk through this line by line, I'm going to have stack push, stack pop. Let me just rearrange that. I'm going to have stack push, and I'm going to look at stack top as well while I'm here. Stack top of S is 0. Yeah? We've set up our initial conditions. We now take stack top of S. This takes S items, which at this point is 0, indexes S elements there, and returns that character. In this case, that character is in fact 0 because all of the elements are 0 at the initial state. And there's nothing on the stack, so we get 0. Okay. Then we push onto the stack. The stack isn't full, so we can continue. Now, at S elements, S items, we put that Z. And now we bump the number of items we have along by 1. I see a few people looking a little worried now. S items starts at 0. In S elements, S items, which is the 0th element, I put that Z. I now bump along S items. Okay so far. But now I take the top. S items is now 1. I now look at the 1th element of my array, instead of the 0th element of my array, which means my logic is wrong. Oh no! And now my logic is correct. And of course, because I've flipped that, I'm going to make the corresponding change. Oh, I didn't do it. Oh dear, how foolish of me. I'm going to make the corresponding change to stack pop. Okay, so now we compile, we run, all tests passed, you are awesome. Woo, fantastic. So, hang on, what? Of course, a logic error again. In this case, what I've done is I've bumped S items down at the wrong time. And now we have the assertion failure I was expecting, which is that stop has set values in a completely, stack pop rather, has set values completely silly. In this case, the completely silly value is this one here. Because we said our initial condition was just to put a 0 there. So let us fix that up. And the other thing you'll notice if you look at the elements here, the first one was the character 0, which we just wrote in. The second one is our letter Z. It's not too much of a problem if those are the wrong way round, but just to make sure that we're right. All tests passed. You are awesome. Now, this is just very, very simple tests. This is a very, very simple test. This does really only one thing. It deals with all of the stack operations on one item of the stack. Yeah, that's not especially interesting. So nominally what you would do is you would go and write a bunch more tests. And as you wrote those tests, you improve your test coverage for cases like the program should go away under these circumstances, or you should return this particular value under these circumstances. You should never remove tests when you write them. So you just get more and more tests. And at the end of the day, what you have is an implementation that is correct and a test suite that is comprehensive. So what we're going to do is now take this. This is concrete, this is horrible, because for all the same reasons we saw before, we have to still deal with the fact that the stack is an object in C. It's a struct there's arrays going on, there's values moving around, we have to hold on to values in ways that we don't ordinarily have to. This is horrible. Concrete types are absolutely painfully hard in this instance to use, to reason about. We've taken a step towards a new level of semantic meaning. We've taken a step towards new ability to state a problem. But we haven't quite gone far enough because we are still tied up a lot in details. So what we're going to do is we're going to make this an ADT. Actually, better, we're going to make this a break for 5 minutes. We're going to take a 5-minute break, stand up, jump around. It is just a jump to the left, as you all well know, and then a step to the right. Jump up and down, get some fresh air. If you've got any questions, come on up and have a chat. We'll have more wonderful fun coming up in just a moment.